Hello guys, welcome back to Maison African Motives, still on industrial electronics N2, working on our revisions. So we are going to have a question that we are going to consider on our direct current theory from the November 2018 question paper. 2.1, we are being asked here to state the Kirchhoff's second law, that is our voltage law. Remember, the first law is about the current, then the second law, that is the voltage law, which states that if you are given a closed loop circuit, like we are given a circuit that is closed, in this case, having a supply voltage, in this case, the algebraic sum of the voltage drops that you are going to have across this circuit will be equal to the supply voltage, which is the applied, or the sum of the applied EMF. So this, we can just have it in words. Let us just have it in words. So I'm simply saying the algebraic. So we are going to have the algebraic sum of voltage drops. Sum of voltage drops. All right. So this is the algebraic sum of voltage drops in a closed circuit. It must be a closed circuit. That's the major part to consider in this case. Is equal to the algebraic sum of the applied EMF, is equal to the algebraic. So we're gonna have the algebraic sum of the applied EMF. All right, of the applied EMF, which is in this case the total voltage in this case. So we're going to talk about the voltages, then equate to the supply that you'll be given. All right, 2.2 are now given the following. The circuit, refer to this figure, given R1 being 3 ohms in this case. So here we've got 3 ohms, R2 again being 3 ohms, R3 being 5 ohms in this case. Then we've got R4 being 2 ohms. Then we've got R5 being 6 ohms in this case. And we are given VT, which is the voltage, the supply voltage of 10 volts in this case. This is what we have on our diagram. So now we are given to calculate the total resistance on the first part, 2.21. Calculate the total resistance of the circuit. All right, how is this circuit actually taken, or how can we analyze this circuit in a proper way? For you not to confuse this part here, I want you guys to take it this way. I'm going to answer it here so that we can properly see what is happening here. If you are to check properly here, we can see that here there's a supply voltage. Here there's a supply voltage that is going to give us two currents from this supply. It is going to give us current 2 and it gives us current 1. So instead of working this diagram the way it is, take your supply voltage down or up. Then these resistors, you take them, because if you present it this way, like this is my supply here. Let's say you present it this way. This is your supply. There is a resistor on the supply here of 2 ohms, which is the R4. Then this is going to give two currents. This supply is going to give us two currents. We have got resistor R6. All right, we've got resistor R6 like this, having our first current, because it's from the supply. The supply is the one that is giving this current. So we are going to give the first current, which is I1. The second current is transferred on this other circuit. So it's one and the same thing, but this one, it's more easier because you understand when you are given a diagram like this. All right, so here for two resistors with a parallel combination here. So we're just gonna have it like this with a parallel combination. So let me have my two resistors a little bit on top. So we've got these two resistors and this one in parallel like this. This is the diagram that we're actually supposed to have in the normal sense like this. Having this diagram, you can simply understand to say, okay, my total resistance in this case, I have to calculate this part here because it is going to be related to the supply. So we are going to find this part, then combine to the supply, because in supply here, we are going to be adding, it will be now in series. So we need first to calculate this. All right, so we are going to combine this R1, R2, and R3 together. How do we combine this? R1 and R2, they are in series. All right, I'm not going to remove this. I want to work with this so that you understand. So R1 plus R2, these ones, they give us the first series combination. These two, they are in series. So let us add 3 plus 3, which is going to be a 6. So we are going to obtain 6 ohms. All right. Being in series, we are going to obtain this as a single resistor now, parallel to this one. So these two, they will be in parallel. So meaning to say we are going to have the parallel combination RP1 from what we obtained from the series circuit and this R3. So it's going to be product over sum. But remember the concept. So it's going to be RS1 times R3 over RS1 plus R3, product over sum. So that is the first parallel combination that we have, which is RS1, which is 6. So that's 6 by the R3, which is the 5 ohm. So that's by 5 over 6 plus 5. All right, so that's 6 plus 5 here, which is going to give us 30 over 11, which is going to be something like 2,727 ohms. All right, so that is our parallel combination from this part here that we combined. So this is the part that I'm saying here, we combined this here. So we are now having a single resistor between these two because we combined this part. We are now just having a single resistor here, this part. We combined everything along this connection, along this, combined everything. So now, meaning to say we are now having a single resistor of 2,7. So that is 2,727 like this. Parallel to this one, that is not across the voltage source, which is the 6 ohm. This one that I placed as current one across the 6 ohm resistor, which is our R5. So meaning to say we are going to calculate the parallel combination that we are now having, this one from the two resistors that we come from, these two resistors that are left. Then whatever that you're going to have, we have to add to R4, which is the one that is the 2 ohm resistor across the supply voltage. This one is the one that you are considering here. All right, so let us have our parallel combination from these two resistors. So this is the second parallel combination that we are calculating, RP2, that is going to be product over the sum of these. So it's going to be RP1 times R5, that's product over sum over RP1 plus R5. All right, so that means our RP2, if we multiply, it's going to be 2,727 times R5 in this case, which is the 6 ohm resistor. All right, everything over 2,727 plus 6 ohm resistor. So that means our RP2, if we simplify properly here, we are going to obtain something like 1 comma, that's going to be 1,875 ohms. All right, so this is the parallel combination that we are obtaining of these two resistors that we see here. So what does it mean? It means we are going to only remain now with a single resistor like this. From these two resistors, we are going to have a single resistor. Then the R4 that we're already having in this circuit, that we already in this part, and the supply voltage in this case. This is what we are just remaining, this being our RP2 and this being our R4. So as we can see, these two are in series in this case because we are talking about the same current flowing. So that means we are simply going to add now to calculate the total resistance, because this is the only part that is left, this RP2 and this R4. So we are going to add. So that is going to be 1,875 plus the R4, which is the 2 ohm resistor. That is the 2 ohm resistor. So that means we have the total resistance of the circuit. So our total resistance of the circuit was going to be 3,875 ohms. So that is how we could have calculated this value. All right. Let's check the other part, the current 2. All right, now we need to calculate current 2 in this case, which is the current 2 here, this one on this side. So in this case, definitely you're going to need the total current. Maybe you're going to use the current divider rule from this diagram here that we see, from this part that we have here. We can easily use this part here. So that means it's easier for us if we have the total current, all right? So 2.22, let us start by calculating the total current. So our total current, remember, that's the total voltage over the total resistance. The total voltage on our circuit, it was 10, is that so? That was 10 volts in this case. This one, VT, total voltage is 10. So there we are going to divide. So that's 10 divided by total resistance, which is 3.875. So that's 3,875. All right, so this is going to give us the total current of the circuit, which is going to be 2,581 in amps. So take note, we have the total current. Now let's analyze from our diagram here to say if this is our total current, the one that we calculated here, 2,581. This is our total current here from this diagram, 2,581. What does it mean? Using your current divider rule, you can find the current 1 or you can find the current 2, depending with which part you want to calculate. So here I'm going to apply the current divider rule. Yes, you can use the parallel. You can calculate the total voltage of the parallel. Then you divide by what? The resistance. But guys, there's current divider rule also to be considered. You need to know the application of the current divider rule. So I said on the current divider rule, the current across this one, the one that you want to calculate, I2, is equal to, you use the result that will propose this one, this total current, it is shared between these two resistors. These are the two resistors which are going to share this current. So you use the opposite resistor on top, which is 6. So it is going to be 6 over the total of these two resistors, which is 6 plus 2,727. Then you multiply to the total current. That's the current divider rule. You multiply to the total current, 2,581. The opposite resistor over the sum of the resistors, meaning to say if we wanted to calculate I1, you're going to use this one on top over the sum times the total current. All right, so that's our I2 is going to give us something like 1,77449, like that. It's 1,774 amps. This is current measured in amps in this case. All right, so let us check the other part, the power consumed by R5. All right, the power consumed by R5. This one, I want us to be careful because on our memo there, it's not given properly. The power that is consumed R5 is supposed to use the current across R5 here, which is current 1 here. We are supposed to use current 1. And from this concept that I was explaining here, if we managed to calculate current 2, we can calculate current 1 because we know that the sum of current flowing toward the junction, because we are concentrating on this R5. So we can calculate current 1 so that we can calculate its power properly. So meaning to say we can calculate current 1 there. Remember, the sum of current from our Kirchhoff's law, it states that the sum of current towards the junction is equal to the sum of current flowing away from the junction. So it means the total current is equal to I1 plus I2. That's I1 plus I2. We have the total current here, which is 2,581. 2,581 is equal to I1, which is the one that we want to calculate, plus I2. Remember, we calculated I2 here, which is 1,774. So that means we can be able to calculate I1, transpose this to the other side so that you can subtract. That means I1 is going to be 2,581. So we are going to have 2,581 minus 1,774. All right, so that is going to be current 1, but this is not our question. Our question is not to calculate the current. So we are going to obtain 0.807 amps. If we have the current in this case, our question is how are we going to obtain the power now? So consider this, guys, from our circuit to say here, you have the power, you have the current on this resistor, which is 6 ohms. You can calculate power from there because power can be given as I squared R. So meaning to say, therefore, our power here is going to be taken from I squared R, which is I1 squared times the resistor, where we are calculating this current, which is resistor 5. And we have current I1 in this case. All right, so meaning to say our power, therefore, across R5, that will be PR5 will be I1 squared, which is 0.807 squared times the resistor R5, which is the one that you're asked to calculate from the 6 ohm resistor. So you multiply by the resistance. That was the concept there. All right, so that means you are going to obtain something like 3.907 watts in this case. All right, so I want you to apply this properly. This is actually the proper way application of the Kirchhoff's law. And even if you wanted to use the DC concept, you're still going to have the same answer there. All right, use the Kirchhoff's current law to calculate the unknown current. Now we are back to that Kirchhoff's. You see the application of the Kirchhoff. They actually want you to use that. So this one is actually having 4 marks for this. All right, so I asked you to use the Kirchhoff's current law to obtain what? Calculate the unknown current, which is in this case, we are given I5. If I1 is equal to 3, so here we've got 3 amps, I2, which is 2 amps, I3, which is 1 amp, and I4, which is 3 amps. So remember from our Kirchhoff's current law that the sum of current towards the junction, which is the sum of current that is flowing in, is equal to the sum of current that is flowing out, which is away of the junction. So you simply need to consider that to say which currents are flowing in the junction. The one that are facing in, this one, it's facing in. As you can see, the arrow here is facing in. So that means I1. Also I2 is facing in plus I2. Also I3 here it's facing in plus I3. Is there any other current that is facing in? We do not have. So these are equal to the ones that are facing out, the ones that are going out, which is I4 is going out, I5 is going out. So this is going to be I4 plus I5. You add the ones that are going out, you add the ones that are getting in. So this means we can substitute our values. We've got I1, I2, everything there. I1 being 3, I2, that is 2 plus I3, which is 1. This is equal to I4, I4 being 3 plus I5. So we want to calculate I5. So as you can see, you can make this the subject, combine these together. That is, we are going to obtain 6. Transpose these 3. So 6 minus 3 is equal to I5. So that means 2 is equal to I5. So that is our current I5 in this case, which is going to be what? Which is going to be 3 there. All right. Why am I getting the 2? That's a 3 there. 6 minus 3 there, which is going to be a 3. So that is our current 5, which is 3 amps. So that was the idea there. That's how you can obtain 18 marks from the application of the DC theory. You need to understand your circuits. Understand your circuits, understand your Kirchhoff's laws, the voltage law, the current law, and also the application of the current divider, especially this one, the current divider rule. I want you to understand this. If you understand the application of the current divider rule, it's going to be easier for you to attempt any typical question. This is what we simply state about the current divider rule like this. If we have got 2 resistors like this, that is where our current divider rule can actually, if this is a parallel combination that you have, and there's a current here that is flowing, which is our total current. And here we have got I1 and we've got R1. Here we have got current 2, and this is our R2. So it means from our current divider rule, I want you to understand this part. The current divider rule is simply stating that the current one, this one, if you want to calculate current one, you use the opposite resistor, which is R2. So it is going to be R2 over the sum of these resistors, R1 plus R2 times the current. Since you are dividing this from the total current, you are going to multiply to the total current. So that's how you can calculate I1. The same applies to I2. If you are calculating I2, you are calculating I2, so you use the opposite resistor on top. That is the concept. So it is going to be R1 over the sum of the resistors does not change, R1 plus R2 times the total current in this case. All right, so this is the one that you are going to use when you are calculating current 2. So it is used on a parallel circuit, of which you can calculate the voltage of the parallel circuit in this case, which is equal to the total current times the resistance of the parallel circuit. After calculating the total voltage, you can calculate I1 direct, meaning to say you can calculate I1 by using the voltage in the parallel divided to R1. If using the voltage in the parallel to calculate I2 divided to R2, this is the alternative way, which is not the current divider rule. This one is from your normal circuits to say voltage in parallel is the same. So you can calculate the voltage of the parallel circuit from the total current times the total of the parallel combination. Then from there, you can calculate I1 and I2. So these are the most important combinations. The application of the current divider rule and the normal way of your calculation from your understanding of the voltage in parallel, that it is the same. So let's revise as much as we can. We still have a lot to learn and a lot to work on so that we prepare for our exams which are ahead of time.